Lesson 3 on Chapter 1 is going to be about continuity. So continuity is a term that we use to describe certain types of functions. If a function is continuous, it is smooth and connected, like this picture right here. If it is a continuous function, you could put your pencil down on the paper and draw it without ever having to pick your pencil up, like you can see on this particular function. But not every function is like that. Some functions are broken apart. They have breaks or holes or gaps in them. And if they have a break, hole, or a gap, then it's considered to be a discontinuous function. So here's 3 types of discontinuity. The first type that you see on the left is called infinite discontinuity. And this happens when at a particular point C, like you can see on this graph, the graph is going in infinite opposite directions at C. So it's broken apart at C, and it's going in infinite opposite directions. Another type of discontinuity is jump discontinuity. And at a particular value C, like you can see here on this graph, the graph jumps from one height to another height, and it's broken apart. And then the last type is called removable discontinuity. And if it's removable discontinuity, it's as if one point's been removed from the curve, from the graph, whatever it is. And you can see that on the third picture on the right. You've got a point that's been removed from that line, and so that's at C, so thus it is removable discontinuity. Now, with that understanding is we have a continuity test. And a continuity test has 3 parts to it. The first part is you have to show that the function is defined at C. I like to call this step A. If the function is defined at C, that's your first part of the continuity test. Now, how do you know if the function is defined at C? You simply put the value C into the function. The second part, call it step B, is to show that the function approaches the same value on either side of C. That is, the limit of the function as x approaches C exists. This is some new notation that we use. And then part C, we have to show that the value that f of x approaches from either side of C that we found in part B, that's equal to the same thing found in part A, f of C. So this word limit in mathematics, really it means approaching in mathematics. So we use the word limit, we abbreviate with the letters LIM to write limits. So here's an example 1. It says determine whether the function f of x equals 2x squared minus 3x minus 1 is continuous at x equals 2. Well, if you look at x equals 2, we have right here a point where the graph appears to be continuous. So if it's continuous, we've got 3 parts. The first part is to find out if f of 2 exists. Well, if you put 2 into this function, looks like we'd get an output of 4 minus 6 minus 1, which is equal to, did I do that right? No, it's 8 minus 6 minus 1, which is equal to 1. So f of 2 does exist. If you put 2 into this function, your output is 1. Then you've got step 2, which says, does the limit of f of x exist? So if you take a look at this graph, as you approach x equals 2 on the left, it's getting closer and closer to a height of 1. And as you approach x equals 2 on the right, it's getting closer and closer to a height of 1. So, does the limit of f of x exist? Yes, because the limit of that function as x approaches 2 on the right and the left both get closer to 1. And then step 3, does the limit of f of x as x approaches 2, does it equal f of 2? Well, yes, because this value is the same as this value. So this is the continuity test. Here's another example. This particular graph you can see is broken apart. It's a piecewise function. We've talked a little bit about piecewise functions this year, and you've also learned about piecewise functions in Algebra 2. So the first step of the continuity test is to ask yourself, does f of negative 3 exist? Well, Can you put negative 3 into this function? If you do put negative 3 into this function, you'd have to put it into the bottom piece, not the top piece, because of this stipulation right here. And so if you put negative 3 in, you would get 2 minus a negative 3. And so f of negative 3 is equal to 5. So first step of the continuity test, show that f of negative 3 exists. We've done that. Second part, does the limit of the function exist as x approaches negative 3? Well, if you approach negative 3 on the left-hand side, you can see you're getting closer and closer to a height of 5. If you approach negative 3 on the right-hand side, you're getting closer and closer to a height of negative 11. So the limit does not exist. And the reason the limit does not exist is because the limit of the function as x approaches negative 3 on the right equals negative 11, and the limit of the function as x approaches negative 3 on the left equals 5. These two values are not equal to each other. It's got to approach the same thing on either side. Therefore, this fails the continuity test, and we don't need to do the third part to show that the limit equals f of negative 3. Here's another example. This is a rational function. A rational function is one that can be expressed in terms of a fraction. Now they're asking us to test it at negative 3 and also at positive 3. So our first step to test it at negative 3 is ask yourself, does f of negative 3 exist? Well, if we put negative 3 in for x, we'd get a 0 on top, we'd get a 0 on the bottom, and that is undefined. So, does f of negative 3 exist? The answer is no. We will not proceed with a continuity test because the function does not exist at negative 3. Now, if you look at the graph at negative 3, can you see what's happening? Let me use the highlighter to help. You can see right here at negative 3, there's a hole in the graph. So what type of discontinuity exists at negative 3? I would call that removable. Discontinuity. All right, now let's move on and let's test it at x equals 3. So if you put 3 in for x, what would you get? So that would give me 6 on the top, and on the bottom it gives me a 0. This is also an undefined value. Since this is an undefined value, let's look to see what's happening at x equals 3. You can see right here the graph is broken apart at x equals 3. And the graph is going in infinite opposite directions at 3. So therefore this is infinite discontinuity.